Okay. Everybody okay? Do you see my slides? Can you hear me?
Yes.
Good. So the first issue is a matter of scheduling conflicts. So we have this conflict on Thursday with the course Internet of Things. The course, unfortunately, is owned by computer science, Informatica. So here people in engineering cannot, sorry about the clock here, 9 o'clock, cannot reschedule it. Do you know how many of you are attending this course? Is it a large number? Does anybody know?
I don't know.
You don't know. So the solution that seems to be the only one is to have our class only on Friday for 3 hours. I'm not extremely enthusiastic about it because it's a matter of attention span. I don't know how easy, actually difficult it is to follow the material that sometimes can be hard, that we discuss here, for 3 hours. So let me have a little bit of additional discussions with people who organize the scheduling, and I'll let you know if this is what we have to do, and apparently there is no other solution. We'll do it this way. What I can try and do is, so I have our class between 4 and 7 p.m. on Friday, a good way to start the weekend. I can insert a break of about 10 minutes after the first hour and 25 minutes or so. So we have two sections of 1 hour and 25 minutes with a break in between to try and rest our brains and my voice as well. It's difficult for you. It's difficult also for me to keep talking for 3 hours and maintain the required concentration. So I will let you know. How do you feel about it? Will it be very hard for you to sit and listen to my rambling for 3 hours? I know it's not perfect. All right, well, I'll let you know. So how many of you are attending now? Let me see here. We have 7 people. Okay. So last time I introduced, where's my pointer here? I introduced the main issue, one of the 2 main issues of the class, which is how we go about calculating the band structure of a solid, starting from the correct way of setting up the Hamiltonian of a crystal, accounting for the degrees of freedom of the electrons and the ions. I think I'll review it today. I'll go again through the same material that I covered last time, because it's very important. For some of you, it may be new material, and there are conceptual issues which are not terribly easy to understand. So I'll go through it again a little more quickly. Of course, please stop me if you thinking about it, reading about it, you have doubts, you have questions, just stop me, and I'll do my best to try and address these issues. And then we'll move into the calculation. So this is the very, very general, high-level theoretical part that we have discussed and we'll review today. And then we go into how do you calculate these things on a computer, of course. Calculations of the band structure of semiconductors go back to, I think, the early calculations on a digital computer were done in 1964 by Frank Herman. Used to be at the IBM labs in Almaden, California. I think he used the muffin tin method. So it goes hand in hand with the development of digital computers. Before, yeah. Is there a question? Is there a question? I can't hear. If it's a question, I cannot hear you. Too far away from the mic. Was there a question or no? No? Okay. Well, please ask anyway. So I'll keep repeating that. All right, so let me review a little bit. The previous lecture, I want to make sure that you understand it, because it's an important issue conceptually. If you grasp this basic concept, you can appreciate the difficulties that we're facing even today with density functional theory. We're calculating structures of nanowires, whatever it's of current interest today, two-dimensional materials, like silicon nanosheets, which is where the VLSI technology is moving to. They're investigating two-dimensional materials, but I think that silicon nanosheets is the way that they plan to go to, whatever is the next node, or whatever the 2 nanometer node, whatever it's called. So there are big issues, because moving away from bulk, these problems become extremely important. So let me go quickly again through the same slides that I showed last time. By the way, I will reorganize the slides according to the dates, and I will post them on the MS Teams, on the website of the class, and so you can look at them again. So this is the, in its full glory, the Hamiltonian of the system that we have to deal with, that we presented last time. We have a term, the first and second term, which represents the kinetic energy and the Coulomb repulsive energy between the electrons, whose coordinates are, canonical coordinates are given by their position, little r, and little p is the canonically conjugated momentum, the usual momentum. And the index I runs over all electrons in the system. I remind you that this sums whenever we talk about interactions among particles of two-body interactions. This sum means that we don't count twice. And that's why there is a factor of a half, the interaction between electron I and electron J. And also we exclude electron I itself into this sum. Otherwise, this thing will diverge. It's the self-energy. We have the same thing for the ions. They also interact, of course, they bind. So there is an interaction U, given this potential U, which of course includes also the effect of the electron clouds that we have around the nuclei. There's the kinetic energy of the ions. And of course, there is an interaction between the electrons and the ions themselves. We have to make lots of approximation. It's obvious that this expression is extremely complicated. So this is again the list of approximations that we're going to make in order to make the problem solvable, treatable in a numerical way. So the first is the Born-Oppenheimer approximation, the adiabatic approximation, which relies on the concept, on the idea that the mass of the electrons is much smaller than the mass of the ions. So the ions move much more slowly than the electrons, which means when I move an ion, think about the thermal excitation of the lattice, the motion of an ion will be equivalent to a phonon, acoustic or optical, whatever. And the electrons follow adiabatically, instantly, the motion of the ion. So we can decouple these two expressions. Essentially, when we look at the electronic component, kinetic energy, Coulomb repulsive energy among the electrons, and attractive energy to the ions, we can treat the position of the ion as a parameter, meaning that the electrons follow instantly any change on the position of all of the ions that we have in a crystal. And so we can solve the problem separately for the electrons and for the ions, assuming that here, the potential that describes the interaction between the ions, the binding energy of the crystal itself, if you wish, contains the motion of the electron, which is treated as instantaneous. So it's a fixed charge that follows the motion of the ions. Of course, you understand that this is a repulsive interaction between the nuclei, but we have the bonds in between. The charge of the ions of the core, the nucleus itself, is screened electrostatically by the core electrons and the valence electrons, and we treat that as responding instantaneously to the motion of the ions. So we can separate the two. The total Hamiltonian is split into a lattice Hamiltonian that deals only with the ions, and the electron Hamiltonian, which deals only with the electrons. The ions see the electrons as moving instantaneously. The electrons look at the ions as moving so slowly that we can think them fixed. And the first step will be to fix the ions into the their equilibrium position, which is whatever is the lattice geometry that we're dealing with, and we treat it as a parameter, and we'll deal only with the electrons when the ions are frozen at t equals 0. And then we will look at what the lattice Hamiltonian is. And of course, eventually, we will have to deal with, with the fact that electrons and ions can interact away from 0 temperature. Electrons can emit or absorb phonons, so they bump into the motion of the ions which are excited at the non-zero temperature. They're thermally excited, and that we will deal with in perturbation theory, considering only small displacement of the ions from their equilibrium position. That will not be enough, so we will concentrate first on the electron Hamiltonian, and we'll deal with the band structure, which is the excitation spectrum of the Hamiltonian. This will be an extremely complicated problem. We have a many-body system with a wave function which depends on the coordinates of all of the electrons. So we'll split the wave function, we'll factor it into a product of single particle wave functions. We'll look at the total interaction between the electrons and the ions and the Coulomb repulsion among themselves. We'll treat it in a mean field approximation. So we'll sit with one electron, we look at all of the other electrons and say, well, the potential due to these other electrons and the nuclei is simply a mean field. I look at the square of the wave function, which is a stationary state of all of the other electrons. I calculate the charge due to these square wave functions and solve Poisson equation. This will give me a potential, and this electron that I'm sitting on will feel that potential, the average potential of all of the other electrons. This ignores many things. First of all, assumes that a wave function can be factored into, rather than a many-body wave function, is the product of many single electron wave functions. And we also ignore the fact that electrons are fermions. The total wave function has to be antisymmetrized. So there is an improvement that we can make immediately to this mean field approximation, which is called the Hartree approximation, by accounting for the fact that the wave function has to be antisymmetrized, which means that if I swap the indices of two electrons, any pair, I swap two indices, I get a minus sign in front of the wave function. And this is the Hartree-Fock approximation. Very good, very nice. We can study many electron atoms with this way. We can study some molecules, not too complicated, but still the problem is extremely complicated. And so we'll have to do something else. When we move to a solid, we have to do something beyond Hartree. Hartree-Fock, it's correct, but it's not treatable. It's too complicated. So what we will do, we'll rely on some fundamental theorems that tell us that the ground state properties of a solid are determined exclusively by the electron charge in its ground state. And that leads us to density functional theory, which finally makes the problem solvable, with some shortcomings that we will discuss in the course of the lectures. So let's go quickly now about, again, what I said. We have a full wave function, which is a messy object. These little r and big R are the set of all of the coordinates of all of the ions, the big R of all of the electrons, the little r's, and we split it, we factor it like a separation of variables, thanks to the adiabatic approximation. We assume that the electronic wave function depends on the position of the ions as a parameter. So we don't have to solve the Schrödinger equation for the ions simultaneously with the Schrödinger equation for the electrons. So we separate the two problems. And you can have some simple argument showing that indeed, in a time-dependent fashion, the error that we make is of the order of the ratio between the electron and the ionic mass, which is at least 4 orders of magnitude, usually more. The heavier, if you go to antimony, clearly, is going to be some 5 orders of magnitude or more. So we're not making a big mistake. Okay, the ionic Hamiltonian, I described quickly how you can do it with it. We will deal with it later on. We will need it to talk about phonons, and we will need it also to talk about dielectric screening. So how to calculate the dielectric response of a system. I have my solid, I apply an electric field at a given frequency with a given spatial variation. How does the system respond? What are the polarization charges that arise, and what is the total field that I have? So we'll discuss it later on. Last time I just showed you that we will use what's called the harmonic approximation, so that we expand the potential energy between two ions up to the second order. First order term vanishes because we're at equilibrium, so only the second order, and then we will be able to solve the problem. So this will delay to later. Okay, the problem that we discussed is now how do we deal with the electronic Hamiltonian? So we split it into the sum of the Hamiltonians of each single electron, and then we can use a variational principle, if you wish, by considering this mean field approximation, which means that a single electron Hamiltonian is composed by a first term, which is its kinetic energy, the interaction of the electrons with the lattice, which is a periodic function, as it's expressed here, because it's the sum of the potential due to each ion which is sitting in its lattice position plus the displacement from the center coordinate of the unit cell. And then we have this messy issue, which is the electron-electron interaction, and we'll assume a mean field approximation. So for a given electron I, we sum over all of the other electron j, the square of the wave functions, which is the probability, the electron probability according to the Copenhagen interpretation of quantum mechanics, multiplied by the charge of the single electron gives us the charge density due to the other electron j. We sum over all other electrons j, multiplying by the Green's function of the Poisson equation, with the 1 over r potential of the Coulomb interaction, and this gives us the potential due to the average charge of all of the other electrons. And this is what we call the Hartree approximation. I pointed out already that we get an equation which looks like an eigenvalue problem, but really mathematically it is, physically it is a little tricky to understand what the eigenvalues mean. And I told you this is not the energy of an electron, it's actually the energy that it takes to remove the electron from the system and bring it up to the vacuum level. So the ionization energy. And we can actually show that if we sum all of these energies, single electron energies, we don't get the total electron energies. And that's because the system is interacting. That is an important thing that I should repeat. If you have a bunch of particles, they do not interact, each particle with a given energy. If you remove one particle, the total energy of the system will be what you had before minus the energy of the particle that you have removed. If the system of the particles instead is a system of particles which interact among themselves in a Coulomb interaction, then this is not true anymore. If you remove one particle, the total energy of the system changes for two reasons. One, you remove the energy of the particle. Good, that's as it was before. But now you're also changing the interaction between all of the particles which remain in the systems. Dielectric scaling is changing. The total charge density of the system is different. So the interaction among all of the other particles now is affected, and the energy so changes by an additional amount. So that's why you cannot just say that the energy of a single particle summed over all of the particles gives you the total energy of the system. There is the interaction part, which is what is shown here. The total energy of the system is the sum of this single particle energy minus this interaction part that you change when you remove a particle. All of this is nice and dandy, however, it's not correct because we're ignoring the fact that electrons are fermions. We will discuss it later on, spin statistics theorem, they obey the Fermi-Dirac statistics, which means that the total wave function of all of the electrons has to be antisymmetric when you swap the indices of two electrons, and so we can write it as a determinant, let's call the so-called Slater determinant, that makes sure that if we combine this, this is an extremely messy thing, right? It's an electron factorial terms, so it's as soon as the number of electrons grows beyond 5 or 10, it becomes an extremely large number. But anyway, formally, this tells you that you can actually write the wave function this way, and it satisfies the anti-symmetrization requirement that we have. Of course, here I'm assuming that the electrons are antisymmetric in their spatial part. They're spin 2, so it's even more complicated than that. If the electrons have parallel, say 2 electrons, if they have parallel spins, then their spin component of the wave function is symmetric. So the spatial component has to be antisymmetric, which is what we're dealing with now. However, if the electrons have antiparallel spins, which are in a singlet angular momentum state or spin angular momentum, then their spin wave function is antisymmetric, so the spatial component has to be symmetric. We have more, particularly for many electron systems, way more possibilities of mixing up many electrons with antiparallel spins, with parallel spins. So usually this is a good approximation, but it's not totally correct, right? For now, let's leave it at that. So Alexander Fock, I don't remember when he did it, but anyway, he formulated the problem variationally, which means he looked at minimizing the expectation value of the single electron Hamiltonian over these many electron wave functions. And he found that in order to do that, you can write your single particle, let's call it Schrödinger-like equation. It looks like a Schrödinger equation in this form, which is extremely complicated. This is the usual R3 component, the kinetic energy of the electron, the interaction with the electron, between the electrons and the ions in a crystal, the Coulomb repulsion in a mean field approximation. This is just the potential due to the mean field of all of the other electrons, sum over all of the other electrons. And again, I remind you that this means that this sum should be intended as excluding the double counting of I and J and I were the same, okay? In addition to the R3 component, it's kind of intuitive. You swap now the indices of two wave functions, this and this, and you have a reduction of the repulsion. That's why this term is negative. So it's an attractive term, which is called the exchange energy, and it's caused by the fact that electrons which are in an antisymmetric wave function tend to be a little farther apart than what they would be if they were classical particles, which is what we have assumed here in taking the Hartree formulation. So this reduces the total energy of the system because these electrons tend to repel each other a little bit. This works much better, in particular if you use this procedure that you can use exactly as it is written here to solve a many electron atom. You find results which are in much better agreement with experiments than what the Hartree model does. The Hartree model is really bad. It misses the energy. So if you try and calculate the spectrum of a many electron atom, calculating using only the Hartree model, you're off by as much as a factor of 2 in terms of the binding energies. This corrects this problem significantly. Notice that this is a complicated problem mathematically. This is a nonlinear integral differential eigenvalue problem. It's nonlinear. The unknowns enters in the integral here and enters also in an even more complicated way here. This is your unknown psi of I. So it's an extremely complicated problem. You can solve it by iteration numerically. You start from some guess. You neglect, for example, the Coulomb repulsion at first. You solve your Schrödinger equation as if you were, excuse me, the hydrogen atom, except that now you have a nucleus which has a charge which is Z, the atomic number of the ion that you're dealing with, the atom that you're dealing with. You find some wave functions. You start plugging these wave functions in this expression, and you solve the problem again. So you get a first order correction to the wave function, and you keep iterating until eventually you converge. This is doable in a many electron atom because we don't have that many electrons. In a solid, it will be extremely hard to do. And that's why you need something else. So what we do is, okay, this we know how to deal with. These are the simple terms. The complication is the Coulomb interaction among the electrons. This has the Hartree component, and then there is an exchange component, and there is something else. There is the correlation energy, which is what the error that we're making by assuming that, for example, the many electron wave function is a product of many singular electron wave functions. So how do we deal with this? And that's where these theorems from density functional theorem, this theory can come from, and they help us here. We write the terms that we know how to solve. That's okay. Kinetic energy, interaction with the lattice, accounting for some screening of the ionic charge and ionic potential. And then we express that those messy integrals in terms of the functional of the electron density. And this is thanks to the Hohenberg-Kohn theorems. They tell us that if we look at an electronic system, their ground state is determined uniquely and completely by the electron charge density, nothing else. So as I reminded you last time, here this is not obvious. We have that this Coulomb term, the interaction among the valence electrons, depends on the wave functions, not just on the square. This depends on the square, but this exchange term depends on the wave function itself. So the phase of the wave functions, all the phases, matter quite a bit. So in principle, we would need apparently more information than just the square wave functions. It is probably related to the usual random phase approximation. When we have many degrees of freedom, the phases of many electrons tend to cancel in a destructive way. And so this is where this theorem comes from. You don't have to worry about the phases of the wave functions. Their square magnitude is sufficient, which is the periodic component, if you wish. And this is the theorem which guarantees that we can solve a single electron problem in this way. This is, if you want, is the final results. We have gone through this many approximations: the Debatic approximation, the single electron approximation, the Hartree-Fock of the mean field, the Hartree-Fock, which is the antisymmetrization of the wave function, and finally, thanks to the Hohenberg and Kohn theorem, we can write this in a way that seems to be relatively simple. It's still a nonlinear problem because it all depends on the square of the wave function. So here we need information of all of the states, all of the bands that we will find, the core electrons, the valence electrons, if you're dealing with the conduction band and so on. It's simple. I remind you that the most important thing is that the Hohenberg and Kohn theorems are related, or they talk about the ground state, valence at zero, valence bands at zero temperature. Conduction bands are excited states. So in principle, we do not have the right to expect that what we're doing is correct when we're dealing with the conduction electrons. Okay, so the problem has been reduced to this, and the total mass about the exchange and correlation is represented by a functional of the electron density. It's nonlinear, it's complicated, okay, but it's solvable. Again, what is the value, the physical meaning of this eigenvalue, single electron energy? I remind you that we have to go back to what is called the Koopman theorem that says that this is the ionization energy, although it's a habit that everyone has of treating this as the energy of a single electron. But again, it's an interacting system. So if I remove one electron, the energy of the system changes by more than just subtracting the energy of the electron that I've removed. This is not enough because that's very good, again, nice and dandy, but we don't know what to do with this. So what is this function? Hohenberg and Kohn tell us that it depends only on the charge density, but they don't tell us how it depends on that. So that remains an open problem. So the first approximation that was done historically was by Walter Kohn and Lou Shan, and they said, well, why don't I look back at what is the exchange and correlation function in a homogeneous electron gas? We know what that is. Lots of people worked on the problem, but mainly it was Murray Gell-Mann and Bruckner who did it. And they show that the exchange and correlation functional is a function of the cubic root of the charge density, okay? Not as a cubic root of the charge density is 1 over the length. So if you multiply by the charge divided by 4 pi epsilon 0, you get essentially a Coulomb energy, potential energy. This is the exchange and correlation in a homogeneous electron gas. If I assume that in a crystal, the charge density doesn't vary too fast spatially, it's kind of quasi-constant, very smoothly, then I can use the local density approximation and say the exchange and correlation function that I will use here, even in a homogeneous system, will be given by the expression that I get from the quantum electron gas. So I would plug here some number which is a constant multiplied by the cubic root of the electron density. And this is density functional theory in Kohn-Sham approximation. I told you, just to give you an idea, we're not going into details about what the FT does now or how to go beyond the FT, but it is surprising that the FT doesn't make a bigger error in this local density approximation in calculating the gap. If I calculate the gap of silicon or germanium, I usually get most of the materials. This local density approximation gives me a gap which is about a half of what it should be, what is observed to be experimentally. As I repeat, you have no right to expect anything about the gap because you're dealing with excited states using a theory which is valid, or at least has been shown to be valid only for the ground state properties. So I expect that the valence band will be treated correctly, that the position of the ions may be determined correctly, but the fact that the conduction bands is calculated to be roughly correct within a factor of 2, it's already amazing. Yet people have tried to go beyond the local density approximation, correcting that, using the generalized gradient approximation. It improves. Nowadays, since a few years, there's been a variety of hybrid functionals that have been proposed to improve the expression of the exchange and correlation functional. It now becomes non-local and blah, blah, blah. And this improves quite a bit. Actually, the so-called HSC hybrid functionals give a very good expression for the band gap. If you go higher up in energy, things are beginning to look not too good either. But again, we're trying to improve on a theory that is only with the ground state, improve the situation, the prediction for excited states. So it's a kind of a hopeless situation, and it's amazing that it works as well as it does. All right. So this is a brief review of what we did last time. I repeated it because I think it's very important to understand how many approximations we're making, what are the possible drawbacks that we might expect when we use this, and we're not done yet. I will show you some computational examples dealing with situations which are with approximations, further approximations, sort of empirical, and we'll give some computational results. Talking about bands, we discussed last time a little bit hand-waving how we expect bands as coming out from the fact that if I bring two atoms together, their orbitals begin to broaden. They split into two. If I bring many atoms together, I create a band. The band is just the broadening of each atomic orbital, the energy of each atomic orbital. The gaps are just a remnant, if you wish, of the fact that we have discrete energy levels in an ion with a gap clearly between any two energy levels. The bonding states will correspond to the conduction band, the valence band, sorry, and the anti-bonding states usually correspond to the conduction bands. Okay, there's a lot of talk, but the basic thing I want to remind you is that having calculated the band structure, we know how many electrons we have per unit volume, so we know how to fill them up according to Fermi-Dirac statistics. We can count the states, put electrons into many states. At some point, we run out of electrons. The energy at which we run out of electrons is called the Fermi level, the Fermi energy. It's not exactly the same thing. I'm a little bit sloppy in my nomenclature. And we can have different situations, as you know. We can find that the Fermi level is at the end, if you want, of a band. So we have a situation in which we fill completely a band, and then we have an higher bands, what we call the conduction bands, which are empty. This is an insulator. In general, we can have the same situation in a semiconductor. Insulator and semiconductors are essentially the same thing in principle. Let's call them dielectrics in general. There are materials in which you have a gap. You feel, as it happens in silicon, for example, as I showed last time, you feel all of the bonding states. For 2 electrons, you have 8 electrons. For 2 ions, you have 8 electrons, 4 for each silicon atom. They fill the 8 bonding states. The 8 anti-bonding states, which constitute the conduction bands, they are empty because you run out of electrons. It's an insulator in practice. You have a gap. It's a matter of temperature. If this gap is very large compared to kT, the thermal energy at temperature T, then there will be no electrons which can be thermally excited to go into the conduction band. If you have a gap instead which is small, it's not smaller, but it's not that many KT big, say germanium, which is 0.6 electron volts, the gap, KT is about 25 millielectron volts. So yes, it's much bigger than KT, but not hugely big. So you can have at some finite non-zero temperature, you can have a finite density of electrons that occupy the conduction bands. And you can, of course, manipulate these dielectrics with a gap which is not too large by inserting impurities. Say in silicon, you can put for a phosphorus or boron, which have 5 or 3 electrons. So you can either add electrons or remove electrons from your silicon crystal, and this will give you a finite occupation of finite density of electrons in the conduction band if you put phosphorus, of lack of electrons or holes in the valence band if you put boron. And so by doping, you can actually control the amount of free carriers that you have, so the conductivity, blah, 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 and this leads to electronic devices. If the gap is too big, this doesn't work, and that's why in practice one makes a difference between the two. You cannot dope silicon dioxide. The gap is just too big. You can try and dope it, but the energy levels will be too far away from the conduction bands to induce any density of electrons. You can have instead a situation in which instead of filling completely a band and then hitting a gap, now you can have a situation in which 2 bands overlap, and then if you fill one band, they can spill into the other band. This will be what usually called a semi-metal. Or you can fill a band and then you have electrons left over, like in aluminum, and then you fill the next higher band, which you can call it conduction band, but actually they're valence electrons which populate it. So in this case, you have a metal. And the difference, of course, is the conductivity. At 0 temperature, if you take a dielectric and apply an electric field, nothing happens. No current flows because electrons in the band cannot acquire any kinetic energy because there's the gap. They're full, every state is full. They cannot occupy 2 electrons in the same state, so they can't move. Motion means additional kinetic energy, so no current flows. That's why we call them insulators. Of course, if you dope a semiconductor, if you have few carriers in a conduction band by thermal generation, then of course you have some small conductivity. For a metal, instead, you have a full conductivity. Semi-metals are actually extremely interesting nowadays. They are of a high interest. For example, in group 4 materials, something like tin, lead to some extent, they're actually semi-metals. So their conductivity is not as high as, say, aluminum or copper. And they're interesting because if you put them in a 2-dimensional situation, okay, lead doesn't exist, it lumps into droplets. But if you put a single layer of tin, for example, it acquires extremely interesting physical properties, topological insulators, and quantum spin Hall effects, and so on. So they're materials which are have properties which simple full metals do not have. So they're extremely, extremely interesting. Okay, I will not spend too much time into this problem. One problem that you may want to read, it's in the notes and so on. I realized that I forgot an H bar in the formula that you can find in the notes, so I've added it here. You can try and look at where the bands and the band gaps originate by solving a 1-dimensional problem. So you have a 1-dimensional lattice. Historically, the simple square wave potential, if you wish, which is called the chronic Penny model, is solvable, well, graphically in some sense, and it's relatively simple. So you assume that you have a lattice, so to speak, in which the ionic potential, is rather than being a Coulomb potential, is replaced by a square well. So you have a square well whenever you have an atom. There is a periodicity, which is given by this distance, the thickness of the barriers between the 2 ions, and the width of the well. So A plus B will be the periodicity, and you repeat it periodically. So once you know A, you know B, and you know the depth of the potential well, you can solve the problem. Another problem would be instead to take a constant potential, but in this position put a delta function with some strength. So some constant c times the delta function of the position, delta functional of the position of the ion that you specify. And then you can solve the problem in a similar way. So the idea is to write Schrödinger equation. In this case, we can write it separately in this region, where the potential is U0, and in this region, in the well, where the potential is assumed to be 0. So you have in region A, so to speak, the wave functions AA, which are the function in the well, where this alpha is just the wave vector, or the wave number, because in one dimension in this well. You can do the same in a barrier B. You have to be careful, because now you solve this equation, but this beta, which is the wave number in a barrier, can be real or imaginary, depending on whether you are above the energy U0 or in the energy U0 in which you have evanescent exponentials of your solution. So the idea is you solve these Schrödinger equations in terms of a linear combination of two exponentials, one moving forward, one moving backwards if you propagate, or one decaying going towards the right and one decaying towards the left if you are in a barrier. And then you have to match the boundary conditions. You have to have that these wave functions calculated in a well and in a barrier have to be continuous at the interface, and their derivatives have to be continuous. So you have two equations in two unknowns. It's periodic, and so you can do your algebra now. I will not go through the details, but at the end you find that there is a relationship between the energy that you specify. You set an electron energy, could be here in a barrier, could be here, a propagating electron, a free electron. So depending on whether your energy is bigger than U0 or smaller than U0, always bigger than 0 because we have no solution for negative energies. You do the algebra. Unfortunately, you end up with an equation which is transcendental. If you want to solve it for alpha, you can solve it numerically. And you find actually that if you change alpha, so if you change the energy, the left-hand side, you see it has to be equal to a cosine. So this can be smaller, the magnitude of the left-hand side can be smaller than 1. And then you have a value of the energy as a function of k, which is the wave vector of your electron. Or if this number is bigger than 1, the magnitude is bigger than 1, you have no solution, which means you have a gap. There are some values of the energy. Remember that the energy is hidden in the expression for alpha and beta over here. Right? Alpha is this number, and beta again has the energy here. So there are values of the energy for which you have no solution, and this gives you the band gaps. So it's an interesting problem. I suggest that you look at it in detail. Maybe if you dare and you want to replace, take a potential, a flat potential, but every B plus A, or every distance A, forget the B now, put a delta function with a negative coefficient in front, minus C, delta of x minus x sub n, where n is the position of your ion. Then the situation will be similar. You have to have a continuous wave function, and the condition about the derivative is such that the derivative of the delta function has to be discontinuous. The two derivatives on the minus side and the plus side have to be equal and opposite, and their difference has to be equal to 2 times c, which is the strength of the delta function. You can do the algebra, it will be very similar. I recommend that you do it. If you have questions, please send me an email, ask me, and we can talk about it. Any questions so far? Am I still online? Do I exist? Usual question.
No, bro.
Okie dokie. So I exist. Good. Okay. So let's move on now. So everything is nice so far. We have looked at the theory. Very nice. So I remind you where we are. We are here. Very nice. So I have derived this equation. In some way, shape, or form, I can write some form for my exchange and correlation function, so I can solve my equation. How do I solve it? It's an interesting problem. It's not a simple eigenvalue problem I can plug on a computer like this. So it's a little more complicated. So I want to go now into numerical methods that have been thought of in order to solve it. Some of these methods that played a bigger role historically, such as the muffin tin, for example, they're not used much anymore. They were developed in the days before digital computers, where you had to face that single electron wave function with a wave equation with the exchange and correlation function. I had you to think of how to solve it by using paper and pencil. So a totally different mindset on how to reformulate the problem. After the war, with the advent of digital computers, things began to change, and people started thinking of ways in which the problem could be solved with a digital computer. Even then, though, we are talking about 1960s when these calculations began feasible for the first time. Nowadays, if you want to solve numerically an eigenvalue problem of the order of 100,000, a rank 100,000, even a million, depending on how the matrix is shaped, we can do it, sometimes even on a laptop. In those days, finding an eigenvalue problem of rank 10 or 20 was already a chore. It was at the limit of what digital computers with vacuum tubes could do. I'm thinking of the computers such as the ELIAC, the ENIAC, and so on. Some of these approximations and some of these methods have their roots in an age in which people had to be smarter in some sense. They had to think about how to simplify the problem and extract the basic physics, the core of the physics. When computers get too powerful, one tend to be mentally lazy and just plug it in a machine and see what happens. Okay, you don't understand as much, I claim, but that's my personal opinion. Anyway, the first idea that comes to mind is, okay, let me look at this equation again. Okay, let me assume that somehow I can lump the exchange and correlation functional and the Hartree component. So I have my ionic potential. I put everything which is related to the charge density of all the other electrons, I lump it into a lattice potential. I don't know what it is exactly. We'll think about how to formulate it. But what I know for sure is that this object, VLAT plus the exchange and correlation functional, they are periodic. They're periodic functions with the periodicity of the lattice. And that's because we know that this has to be a function of the density, and we know that the electron density has to be periodic. So I may not know the particular form of this object, but I know that it has to be periodic. So let me call now VLAT this entire thing. This is the lattice potential, including Hartree, exchange and correlation, in addition to the ionic potential. So essentially, I have to solve an equation of this form, where this is, I may not know what it is, we'll talk about how I can approximate it or I can calculate it, but formally, this is the equation that I want to put in a computer, okay? I know that since this is periodic, I know from Bloch theorem that the wave functions have to have the Bloch form that represent the periodicity of the lattice. These are the G vectors, the vectors of the reciprocal space of my crystal. So my wave function has to be a plane wave multiplied by a function which is periodic. Remember that we call this also u, little u of r, and this is nothing that, as I told you, the remnant of the atomic orbitals that constitute the crystal. So what I can do is take this expression, plug it here, and this is what I get. Notice that if I take the gradient, I get the I, k plus g. It's convenient if you bring the k in here so they can write it as sum over g of these u's times an exponential of I, g plus k dot r. So if I take the gradient, I get k plus g as a vector. If I take the Laplacian, I get I, k plus g dotted I, k plus g, which gives me minus the square of k plus g. The minus goes away because I have a minus here. Okay, so this is what happens when I plug this expression into the first term. And of course, I have to carry this sum over the g vectors. This I simply multiply the lattice potential by the wave function, and this is equal to E times the wave function. Good. Now the usual trick is the usual thing. I want to convert this equation into a matrix form. It will be an infinite matrix because the sum over G extends for an infinite number of G vectors, all of the vectors of the reciprocal lattice. But eventually I can cook up some argument why I can stop at some particular G. So we'll have a finite matrix. So a finite eigenvalue problem in matrix form. So how do I go from here to a matrix? Well, it's the idea of Fourier transforms, the same idea, converting a calculus problem, a differential equation, into an algebraic problem, linear algebra in this case, because it's a linear equation. So what I do is I project this expression into these basis functions, okay? So I multiply left and right by e to the minus ig prime r, and I integrate. When I say project, what I mean is multiply by the complex conjugate and integrate, which is the dot product in a Hilbert space, if you wish, or in a functional space. So if I do that, I can manipulate my things and find by standard techniques. If you do not know how to get there, try and let me know. But you understand that if I multiply this object by e to the minus ikg prime, ik minus g prime, and I integrate over the entire volume, I get e to the I g minus g prime dot r, which gives me a delta function of g minus g prime. Okay, so if I sum over g, I get a delta. Here things are more complicated. I will get, if you want, a Fourier transform of this potential over g minus g prime, and here I get the usual delta function, and this is what I have. So it's I've rewritten this equation, bringing the two delta functions that I have, which is this term and this term on one side, and then isolating the contribution. And this Vg, as I said, is just the Fourier transforms. Is what happens when I multiply by e to the minus g prime, this equation, okay? And I get the integral over e to the I g minus g prime, or vlat, multiplied by these objects, which I have in front of here, right? And so this is exactly the Fourier transform. V is the volume of the entire crystal for now. We have to be a little bit careful about normalization volumes, okay? So what I have is a linear system, which is an eigenvalue problem, if you wish. It's a homogeneous linear system, infinitely many equations, because I have an infinite number of G's. These are, if you want to look at it in terms of a matrix, it's a diagonal. In the diagonal, I have this term, which is the kinetic energy minus the total energy, and then I have off-diagonal terms. The V0, which is the average potential of the lattice, actually, it's an issue. It's non-zero. Okay? I took it out, so it will appear also in the diagonal. So you know from linear algebra that if I have a linear system, homogeneous, I can have a solution which is non-trivial, which means not zero, not all zeros, only if the determinant of the coefficients is equal to zero. This is what we call usually the secular equation of a linear system. And so we must have that the determinant of this matrix, if you want to look at a matrix, has to be equal to zero. And this is what is going to give us the eigenvalues. Once we have, so the eigenvalues are the bands. Remember what we're doing here. I plug a wave function with a given k vector. For a given k, oops, I'm sorry here. I lost the pointer. Okay, for a given k that I plug in here, I get a different e, a different eigenvalue. So I get my dispersion, which is the energy wave vector relationship. A parenthesis. It's called dispersion because of what the terminology that is used in electromagnetism. If you have an electromagnetic wave in vacuum, you know that the group velocity and the phase velocity of this wave, they're the same. And that's because the relationship between the energy, h bar omega, or h nu, of your wave is equal to the speed of light times k, the k vector of the light, of the photon. So it's a linear relationship. And since the phase velocity is just the energy divided by k, and the group velocity is the derivative of the energy over k, for a linear relationship, they are the same. if you consider electromagnetic waves in a dispersive medium, which means has an index of refraction that depends on wavelength, and so on k vector, then you know that the group velocity and the phase velocity are not the same anymore, which means that if I have a packet, a light packet, in vacuum it will stay the same. It will just propagate at the speed of light. In a dispersive medium instead, it will disperse, and that's where the name comes from. It will broaden because each wavelength propagates at a different velocity. For electrons, usually, for free electrons, E, you see that if I ignore the lattice, I get that E of k is equal to h bar k squared divided by 2m, which is p squared over 2m, which is 1/2 mv squared. So this is a free electron. The energy depends on the square of the momentum, so on the square of the wave vector, which means that the group velocity and the phase velocity for a free electron differ by factor of 2. So the medium is dispersive. So as a habit, one talks about the E versus K dispersion relationship as a dispersion, the electron dispersion, and about all other excitations that we'll talk about, phonons and photons as well if you are not in vacuum. That it's called also the dispersion. Okay, and the parentheses. Okay, so we have reformulated the problem in terms of a big matrix. So this is an eigenvalue problem. If you look at this problem and bring the E on this side, you see that this matrix, which has diagonals h bar squared over 2m k plus g, where g runs over g1, g2, g3, g3, all the g vectors that you have in a lattice. And you have off-diagonal terms, which populate the rest of the matrix. This is a matrix which is infinitely long downwards and towards the right. Okay, so it's an infinite matrix. This matrix applied to the U's for a given k, G is the index that labels the element of your column vector, is equal to E times U. So it's an eigenvalue problem. It's an infinitely big eigenvalue problem. It's an eigenvalue problem. So we have transformed a calculus problem into an algebraic problem, which is what Fourier transforms do, after all. Okay, good. How do we solve it now in practice? Is it doable? Let's go back to the inside the brain of somebody who was working on this problem in 1960 and see, can I solve it with the digital computers that I have? So let me calculate this a little bit in more detail. I've not used the periodicity at all so far. Not much. Well, I have used it because of the G's, but not to express this potential. I know that this lattice potential, that's what we said at the beginning, is periodic, right? It's the ionic potential plus the Hartree plus the exchange and correlation, functional, whatever. But no matter what, it is a periodic function. It has to be. So I can write it using explicit its periodicity. Let me write, if I remind you about the notation, big R sub L is a lattice point. Is, if you want, the coordinate of the origin of cell number L, the primitive cell in my lattice. Tau sub alpha, this is the displacement of the ion from the origin of the cell. For silicon, for example, I will have 2 atoms, so alpha runs between 1 and 2. So I will have tau 1 and tau 2, tau 0, or tau 0 and tau 1. Tau 0 will be 0, 0, 0, an ion at the origin of the cell, and tau 1 will be 1/2, 1/2, 1/2, which is, sorry, 1/4, 1/4, 1/4, which is the coordinate of the silicon atom in the primitive cell. This is, therefore, is the coordinate of each atom, each ion in my crystal, for each pair of L and alpha. L actually will be a set of 3 indices, the Miller indices in the 3 directions. This is the potential due to a single ion. This already includes the screening of the valence electrons, the core electrons, the exchange and correlation, the Hartree, blah, 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 so everything, but it's periodic. So I can write it as a sum over ionic lattices. And let me assume that I have a monoatomic lattice for simplicity now. So this ionic potential in principle depends on alpha. If I have gallium arsenide, for example, the V of gallium will be different from the V of arsenic. Let me consider silicon or germanium, in which these 2 V's in the same cell are the same. No big deal, it simplifies the notation and the algebra over here. So let's plug it in. So what is VG? VG will be the sum over all of the ions, ln alpha of the V ions. So what I'm doing is plugging this expression in here. So I have the sum over ln alpha V ion that replaces what I have in an integral. I've just taken the sum symbol outside the integral. And then I'm just writing, to avoid writing too much of G minus G prime, G double prime. This is the set of all vectors in reciprocal lattice. The linear combination of any two of them is another vector reciprocal lattice, so I decided to call G double prime. This is just re-expressing this integral, this Fourier transform, if you wish. So now let me write it explicitly by bringing, remember that this is just changing coordinates now. I replace R with R prime plus R sub L plus tau alpha. So I make this change of variable, okay? So having made this change of variable, there is a term which is just depending on the lattice site, which I bring out, and then I'm left with a term of the, sorry about my German clock, 10 o'clock over here. Okay, so I bring this outside the integral, and I'm left with an integral, which is over this variable here. I change this variable again, and what I have is, sorry, my mistake, I just wrote R as R prime minus R. Okay, anyway, now I have to do this integral. Notice that I have the same integral sum over the lattice ionic coordinates, lattice and each ion in a cell, this factor over here, and then changing the integration variable this way, I can rewrite this integral in this form. Again, a little bit of a manipulation. I'm rewriting the volume of the total crystal as the number of cells that I have in my crystal. I'm assuming finite volume normalization multiplied by the volume of each cell. This, I think, is pretty obvious. I take the e to the minus ig prime tau alpha outside the integral over here, because it does not depend on integration variable, it's a coordinate, and I brought it actually all the way up to the front, and this is the sum over the ions in each cell. So I'm left with the sum over these guys, and I'll tell you in a minute what this is. Well, let's say it now. Remember that the vectors of the reciprocal lattice are defined, if you go back to lecture 2, I believe, last week, are defined such that the dot product between any vector of the reciprocal lattice and any translation vectors of the lattice is equal to multiple integer of 2 pi. I hope you remember, this is the definition of the G vectors, of the vector of the reciprocal lattice. So this is one, by definition, of what the G vector is, what is the reciprocal lattice. So here I'm summing over all cells, so I get the number of cells. So this sum over here simply will cancel the big N that I have in the denominator. And I will be left with 1 over omega, which is the volume of each cell, of this integral. Now, this integral, notice that the ionic potential is a Coulomb potential, but strongly screened. So its range will be the screening length of the potential. I have the ionic core, say my plus 14 silicon, but then I have 10 core electrons around that, so it becomes already a plus 4, and then I have the valence electrons around it. Now, you know the screening, if you don't, we'll see it later on in class, transforms the 1 over r Coulomb potential into an exponential, e to the minus beta r, where beta is 1 over the screening length. So this potential actually is non-zero only on a very short distance around the ion. So I can assume that integrating over the entire lattice the potential of only one ion is actually equivalent to doing the integral over just a cell, because this potential is 0 outside the cell. So making this approximation, you see what happens now. So I'm sorry, let me go back here. This gives me n, and this becomes the integral over a cell divided by the cell, normalized to the volume of the cell, multiplied by this sum, which is a simple sum over the number of ions that I have in a single cell. This is a sum over a few atoms. For silicon, germanium, gallium arsenide, whatnot, this will be just a sum over 2 terms, so not a big sum. So I have re-expressed my potential in this form. This sum depends only on where the ions are in each cell and on a lattice configuration, of course. And this depends only on the shape of the potential. This factors out neatly when the ion does not depend on alpha, which is the assumption that I made before, that I'm dealing with a monoatomic crystal. For a diatomic crystal or multiatomic crystal, it's a little more complicated, but nothing major. Terminology-wise, this object is a purely geometrical object. It depends only on what crystal you're dealing with, body center cubic, wurtzite face center cubic, monoclinic, orthorhombic, tetragonal, whatever it is. But it depends only on the geometry. What is the crystal and where the ions are in the crystal? For example, by doing any diffraction measurement, X-ray diffraction, you see immediately what this is. You can actually classify the crystal structure, you can tell where the ions are, you can get all the information about the lattice constants quantitatively, about where the ions are, just from spectroscopic measurements, diffraction measurements. And this is called the structure factor, okay? S, called S. This instead, okay, it's a Fourier transform at the lattice vector, so it depends on the geometry to some extent, but it depends mainly on the shape of the potential, on what is its charge, how electrons are distributed in the cores, how electrons are distributed in the valence electrons around the core, what is the exchange and correlation function, the Hartree component, and so on. And this is called the form factor. So the structure factor tells you what is the geometry of the lattice, the form factor tells you what is the binding potential of the lattice. Any questions so far? So let me repeat a little bit to make it clear. So we had to solve this messy problem, remind you. Well, simple looking, but really messy, in which I have the single electron Schrödinger-like equation. I use the Schrödinger-like because really this is a little more complicated than the pure Schrödinger equation. This W, I remind you that it doesn't mean what it is, not just an eigenvalue of this thing, although we treat it as an eigenvalue, but its physical meaning is the ionization energy, not the single particle energy. So we have to solve this problem. How do we solve it? We remind ourselves that this potential, the ionic potential plus the exchange and correlation, is a periodic potential. So I use this notation to label all of the potential that I have. And now I have formally a Schrödinger-like equation. It looks very much like Schrödinger equation in a potential which is periodic. Since this system is periodic, I can use Bloch's theorem that tells me that the wave function has to be of this form. It has to be labeled by a vector k. I remind you that this comes from group theory, from the translation symmetry, and so the periodicity of the lattice. That's where Bloch's theorem comes from. So it has to have this form, which is a plane wave times this periodic function with the periodicity of the lattice. I plug it back into my Schrödinger equation and I find this expression, okay? And then I convert this expression, which started as a differential equation with this Laplacian over here, I convert it into an algebraic problem, although semi-infinite. It's a big matrix which is infinite towards the downwards and towards the right, and I rewrite it as an eigenvalue problem. It simply to simplify my life, I go and look at what the periodicity tells me about the shape of this potential, the Fourier components of the potential, which is what I get by multiplying by e to the I minus g prime r and integrating over r. And this is exactly what this is, right? It's a Fourier transform. I've explicitly indicated the periodicity of this potential by writing it this way, by summing over all the ions that I have in a crystal. Then I've done a little bit of a few manipulations. Here I've simply taken the R sub L over here by having added and subtracted big R sub L in the exponential. I've changed integration variables. I've looked at the fact that now I have my Fourier transform, which is the sum over something that depends only on the ionic positions in the cell, the basis of my crystal, something which will give me just the number of cells over here by the definition of reciprocal lattice vectors, and an integral over the entire volume, but actually is an integral over the cell because of the very short range of the ionic potential. So it's essentially the Fourier transform normalized to the atomic volume of the lattice potential. And then I can express it this way: a geometric factor, which is called the structure factor, and then the potential itself, which gives me an idea about the binding property of the crystal. Okay, what's the problem with this? Why can't I use it now? So I have my fancy, relatively simple eigenvalue problem. I can plug it in a computer and be done with this. Okay, the problem is, what is the shape of this object? Remember that this is essentially a Fourier. Let's go back here. This object. This is a Fourier component of the ionic potential. How many G vectors do I need? This gives me the rank of the matrix. Suppose that I want to solve it numerically. Clearly, I cannot use all of the G vectors. Why can I stop at some point? I can hope that I can truncate my problem at some particular large value of G, because the Fourier, only if the Fourier components of V die as G minus G prime, remember it's the difference between these two, the Fourier components of this object die sufficiently fast when G increases in size. If you remember what the Fourier transform means, a spatial Fourier transform, the higher frequencies mean strong variation, fast variation in space. So if this potential is very smooth, then the higher G components, the Fourier components of this potential, will decay very fast. If this potential is not smooth, then I will have lots of components to keep track of. What is this potential? This potential is the ionic potential plus all the screening effects that you want, but there is a 1 over r singularity, which is the Coulomb interaction. Core electrons do not shield the nucleus itself. The exchange and correlation doesn't do anything at r equals 0, at the core, at the nucleus. Now, a 1 over r means that this guy has a derivative at divergence at r goes to 0. A strong derivative at any distance means that these Fourier components are not going to die very quickly. Actually, if I do some estimates by looking at something like this, considering a potential which is unscreened, you need an order of at least 1 million of G vectors. That's not good, because it means that this off-diagonal terms of the potential will not die until I hit G vectors which are extremely, extremely large. You understand that when this is small, I can ignore it with respect to this component, so I get a free electron model. The electrons become free, which you can understand. I have a crystal. The crystal is composed by the potential of all of the ions. If this potential is, say, 1 kilo electron volt deep, that typically would be the potential of a crystal. If I'm dealing with an electron which is a giga electron volts, like the energies that those people in elementary particle physics deal with, this electron will not care about the crystal potential. If you shoot a giga electron volt electron on silicon, it wouldn't care whether it's silicon or nothing. So you recover a free electron. And at that point, you can stop and say, well, I have a free electron. My problem now is decoupled because I have a matrix without any off-diagonal elements anymore. So it's just a big diagonal. For small G vectors, I have off-diagonal elements, but then deep down, it becomes diagonal. So it's decoupled, and I can stop. The higher bands don't contribute anymore to the lower bands, do not affect them. But if I have to carry my G vectors to 1 million or more than 1 million, before I can make sure that this happens, then I'm in trouble. A Coulomb singularity means that the potential goes to infinity, essentially. So I will never get to that point. So in the early days, people were a little bit depressed. That is a very nice way of dealing with the problem, but unfortunately, the Fourier components of the potential decrease all too slowly. And the problem is just too big. Remember what I told you before, in the 60s, when people were dealing with this stuff for the first time, you could hope to solve a 20 by 20 eigenvalue problem. Maybe account for higher bands and some perturbation theory, which is what I did, but And by hand, I don't know if you ever tried to solve a 4x4 or a 8x8 problem. It requires weeks of work with a 100% probability of making mistakes. So it's a serious issue. And then people decided to use different approximations. So the first, by the way, before proceeding, let me say something that I should have said. Plane waves. So this is what we've described so far. I take my Schrödinger equation written this way, and essentially what I'm doing is I'm expanding my unknown wave function into a set of basis functions, which are basically plane waves. Okay, block waves, but they're plane waves. I think that the community is split into two camps. There are those who like plane waves, and there are those who instead like a different expansion. The philosophy behind the plane wave people is plane wave may be laborious, may be a big problem. However, I do not make any assumption about what the system will look like. I don't know what the final solution looks like. I'm not going to make any assumption. So I may have to make more efforts to get to the solution. But once I have it, I know that I'm not missing anything. There is another group of people, let's call them the tight binding or atomic orbital people, and they say, why do you go through all these problems? You know that basically in silicon, the bonding configuration will be made of sp3 orbitals. And maybe you can have some d wave corrections. So why don't you start by looking at atomic orbitals and expand your unknown into atomic orbitals. Chemists call this thing as LCAO, linear combination of atomic orbitals. Physicists call it tight binding. We'll discuss it. So the tight binding people have a point in the sense of saving effort. The risk is, and that's my take, is that you're beginning to make an assumption of what your solution looks like. So I have S, I have P, I have D, I'll ignore the S states. Well, what if they matter? What if in some particular case they matter? In addition, dealing with transport, the fact that you start with atomic orbitals, they carry no current, okay, because they're stationary state. It's an issue. You're dealing now with hopping of electrons from one atomic orbital to the other. So the transport formulation will be, I think, a little bit, I shouldn't say unphysical, but cumbersome. Not so transparent in terms of expressing transport. So I'm a plane wave guy. I understand the tight binding people, and their arguments. They're computationally usually more efficient because they require fewer wave functions, but in some cases, graphene nanoribbons, for example, if you don't do it properly, you run the risk of getting totally wrong results. So one has to be a little bit careful. So we'll continue for a moment dealing with plane waves, but on next week, and I will tell you whether it will be on Thursday on Friday for 3 hours. Frankly, now we've been talking about 1 hour and 20 minutes, and my throat is beginning to be dry. So I don't know if I can talk for 3 hours in a row. So we'll stick to plane waves, but then we'll move and we will talk about tight binding because there are some features of tight binding which are actually very appealing, and they illustrate the physics in some particular configuration, particularly where you're dealing with a situation in which the bonds are tight, as the name says. So in order to obviate to this difficulty that we discussed, yes, I have my problem, my eigenvalue problem, but my Fourier components of the potential now do not decay sufficiently fast for me to ignore them at a sufficiently large G vector so that I can ignore it, but small enough so that the problem is doable numerically. So if I can have a problem which has a rank, nowadays I would say 10,000, 100,000, I would be happy. Actually, I'll show you that there are situations in which you can get good results with only about 100 of these G vectors. But originally, I said in the 1960s, you really needed a very small number. So how can I obviate to this problem? So the problem is due to the fact that the ionic potential does not, the Fourier components do not decay fast enough, because the potential changes spatially too fast close to the singularity. Hold on, somebody said, and that's mainly, I said Herring here, but I think I meant Harrison. It was Harrison here, not Herring. So Walter Harrison had an idea. Do I really need to worry about what happens at short distances? So I'm making a lot of effort to resolve what happens very near the nucleus, close to the nucleus. I really don't care about what happens in the core. This is probably the general philosophy which will lead us to pseudopotential as well. If I'm dealing with silicon, all I care is about the electrons which are in a valence band, and they form those sp3 orbitals, that they overlap and they form the covalent bond that binds the silicon atoms together. So do I care about what happens to the 1s electrons, which are probably 1000 eV down in energy? Do I care about the 2p, the core levels? The 2p are about 130 electron volts down, when I'm really interested in a few electron volts around the gap. So it seems like I'm making a lot of effort for nothing, to get some information that I really don't need. The problem is that I don't know how to formulate the problem without that information. So the idea that Harrison had was, well, we know from the fact that the problem is a Hermitian problem. My matrix has to be Hermitian, otherwise I don't get real eigenvalues. I know that for an Hermitian problem, the eigenvectors are orthogonal. So the conduction band or the valence band states that I'm interested in have to be orthogonal to the core states. So the idea is, why don't I start looking for a wave function which is orthogonal to the core states? So what I do is I define a orthogonalized plane wave, which is my plane wave. This ket k is a block function. I hope that the notation doesn't confuse you. And let me define, I apologize for the notation that is used quite generally in the literature. T is an integer, of all things, which labels the core states. So for silicon, it will be the 1s, the 2s, the 2p. Okay, so we're running over the core states. Alpha is the ionic coordinate, silicon number 1. So this might be a 2p for silicon number 2, for example. I define the wave functions of the core states that in principle I can calculate using Hartree-Fock for an isolated silicon atom, okay, not in a crystal, because the core states are largely unaffected by the presence of the other ions. I hope that my colleagues dealing with X-ray photoemission spectroscopy are not listening, because XPS actually deals exactly with the energy shift of these core levels in a particular environment. But to zeroth order, they don't matter. So I define these states, and then I hope that you realize that this is just the projection operator over these states. So what I'm doing is I'm taking the overlap integral between my block function and one of these core states, and this is the coefficient, the Fourier coefficient over the block states. I subtract all of these core states components from my block state. So this object is an object that by definition is orthogonal to the core states. But since the core states do not matter too much, this should be identical to the correct solution, the full solution, when I'm outside the core. So in a region where the bonding matters and where the crystal structure matters. Okay, so that was the original idea that, I don't know why I wrote Herring here, Walter Harrison had. That led eventually to the concept of pseudopotential. And the concept of pseudopotential is indeed explained in many words here, but let me illustrate it here. So the green is an illustration of this in one dimension for simplicity, on my real potential. The problems are coming from the fact that this thing goes down to infinity, goes to singularity. It decays, especially very quickly because of screening, but when I move close to the nucleus, it blows up in a 1/r fashion. The idea, as I said before, is that actually wave functions which are localized down here, they don't matter. They're energetically too deep down. Clearly, an electron cannot emit a phonon and scatter into those core states which are a kilovolt down. Even the 2p in silicon will be 100 electron volts down. So an energy range which is not of interest to transport. Again, if you're doing XPS measurements, yes, it matters to you, but we're not doing that here. And I'm having lots of problems in handling a eigenvalue problem of a huge rank, only to resolve issues which really do not affect at all what happens here in the region between the ions, where the bonding takes place. So the idea is, let me see if I can find a potential. Let's call it model potential for now. That was coming from the German school of Heine, Animalu, and those guys. Why don't I replace the ionic potential, which a potential, here I chopped it out brutally, but it's rounded off, so it doesn't have very high frequency Fourier components because it is smooth, which is equal to the real potential between the cores. It is different to the real potential in the core. So I will get wave functions which have no meaning, no physical meaning in the core. They're pseudized, it's a model of the wave function, but they are identical to the correct wave function outside. Why do I say that? Schrödinger equation, which is the equation we are solving, is a second order partial differential equation. So if I have the same boundary condition at some point, so suppose that in a sphere around the nucleus, I have the same function and the same radial derivative of the wave function, then the solution, regardless of what it is inside the sphere, will have to be the same outside. So I can find a model potential that gives me incorrect values where I don't care, but the correct values, the correct energies, the correct wave functions, the correct eigenvalues and eigenfunctions outside the core, where the bonding, the chemical bonding matters and where all the crystal properties are determined. I will stop here. The next step will be to explain how I can determine this potential, show you what the simplifications this amounts to, and then show you how actually the calculation of my matrix is extremely simple. I will go through a little bit formalizing how I can get pseudo potentials starting from the orthogonalized plane waves, and then we'll deal with a computational example for silicon, germanium, gallium arsenide, and I'll show you it actually using empirical pseudo potentials. I will tell you what they are, how I can get some good results shown here, for example, for the band structure of silicon, I believe germanium, gallium arsenide, and so forth. I'm running out of voice. Let me stop here. Are there any questions?
No problem.
No questions? I see that there are some professors peeking in.
May make a comment.
You're peeping in my lecture. Ciao, Giorgio.
No, actually, I would like to congratulate you on your ability to extract physics out of mathematical expressions. It's very good. So I enjoyed your lecture a lot.
Thank you. I see that Elena is also here. Okay. All right. So no questions? If not, I will have to inform you about what will happen to the scheduling issue. I think we will have to go 3 hours next Friday. Yeah, with this issue that we have the Internet of Things interfering with our important physics here. Okay.
Let
the recording.
Let us know when it starts, when the lecture starts.
Yes, I'll let you know for sure. I'll let you know.
Thank you.
Very good. Ciao Giorgio, grazie.
Ciao, bye bye.
Bye bye everybody.
Ciao.
Have a good weekend.
Bye bye.
Ciao.
Bye bye.